All right, I have graded what I've received for Lab 2. If you have not turned in Lab 2, please do so as soon as possible. Take a look at the comments for Lab 2. I'm going to go over what a lot of people did, because part of Lab 3 is refactoring what you did for Lab 2. So, in other words, the idea of refactoring is you take code that works and you revise it to make it better. And what makes code better? Maintainability. There are different ways to do things, to be sure. You know, in programming, there's rarely one absolutely correct answer. But I can pretty objectively say if one application, one version of a function requires one line to be changed if they change tuition rates, and another requires 3 lines to change, that the one is better than the other. All right. Or if they change the rules about tuition, if they eliminated the 13 through 18 credit hours, how many lines would I have to change? If the answer is 9, that's not as good as if I only had to change 3, for example. So, although again, I'm not trying to say that there's one absolute correct way, but again, we can make some observations about the best way to do that. And that's what I want you to do in Lab 3, is I want you to review my feedback, review what I'm talking about now, ask any questions that you have, because there are some people who are a little bit different than this, but a lot of people sort of did the same thing. And I want to talk about why it's a reasonable answer, and it gave correct results, but it could be improved. All right. So part of your task for Lab 3 is to refactor your code to make it work better, and then add a few constructors to it. All right, let's look at how the tuition calculation at LC works. All right, here is the tuition chart. And this is where not being in a hurry to actually write code, but to take a minute and to analyze what's going on can work to your benefit. All right? And the whole refactoring process is sort of like going back and revising a term paper after you've written it and gotten feedback and so on. But the way the chart works is like this. There are 3 categories of students: in-county, out-of-county, and out-of-state. There are then sort of 3 zones of credit hours: 1 through 12, 13 through 18, and then 19 through 22. Okay? Now, if you look at this chart, you'll notice that it isn't like these are just randomly generated numbers. There's some sense to it. In other words, for a Lorain County resident, the fee is $118.34 per credit hour. So 2 credit hours is 2 times that. 3 credit hours is 3 times that. 4 credit hours is 4 times that. And so on down the line. All the way up to 13. And 13 credit hours is 13 times that rate. But they give you a bonus in that if you register for 13 through 18 credit hours, you only pay for 13. So in other words, the amount for 13, 14, 15, 16, 17, and 18 are all the same. So you take 13 through 18, you get charged for 13. Now what about 19 through 22? What happens there? Yes?
Well, 19 has the same price as what if 14 is the later.
Exactly. So in other words, 19 is one above the one credit hour more than 18, so you get charged 1 credit hour more than 18. Well, what did you get charged for 18? You got charged for 13, so you're getting charged for 14. A simple way to say it is 19 and up, you get charged for however credit hours you're taking minus 5. So for 14 credit hours, for 19 credit hours, you get charged for 14. For 20, you get charged for 15, and so on. All right? Now, how is out of county and out of state different than in county? Right. The only thing that's different about it is the rate is different. All right? The rules are still the same. So, for example, out of county is 141.49. If you look at that, 2 credit hours is 2 times that. 3 credit hours is 3 times that. Same 13 through 18 deal. Same thing for 19 and above. Same thing for out of resident. The only difference being is that, again, there's a different tuition rate for that. So I'm going to talk about how I would write this code with those observations. All right? Forgetting about the goofy way that we calculate it with the 13 through 18 credit hours, if I were to just ask you, what is the tuition for a student? You would say it would be the rate times the hours. So I'm going to start with that assumption. All right? Tuition equals rate times hours. All right? I don't like the way those things are going. I'm going to do this instead. I'm going to write on the board. And tuition, simply put, is rate times hours. Now, what muddies the water in our case? What muddies the water is 2 things. 2 things is where there's a little bit of deviation here. Number 1 is your rate depends on your residency. Thank you. And number 2 is that the number of hours you get billed are not the same as the number of credit hours that you take. All right? So there's like your credit hours, and then there's your billed credit hours. So 1 through 12, you get billed for every credit hour that you take. 13 through 18, your billed credit hours is 13. 18 and above, it's your credit hours minus 5. So I'm going to change this a little bit to say times hours billed. All right? Let's keep that in mind. All right? I'm jumping a little ahead of myself. Because here's what a lot of students did. They did some variation of this. They said if residency equals in county, actually that should be equals in county, then if hours less than 13, tuition equals hours times, and let me look up the rate, 118.34. Else, if hours are less than 18, no, hours are less than 19, tuition equals 13 times 118.34. Else tuition equals hours minus 5 times 118.34. And then enough closing brackets to match it up. So that would be the section they had for in-county. They would have the exact same section repeated, except out-of-county with the out-of-county rate here, here, and here. Then they would have another section for out-of-state that looked exactly the same as this, except out-of-county, out-of-county rate, out-of-county rate, out-of-county rate. In other words, a lot of students had 3 sections of code that did the exact same thing except for a couple of numbers, except for the tuition rate. All right? Anytime you see code that is duplicated or like really close to being duplicated, that should set off sirens in your head that maybe we can do this better. All right? Maybe we can write a function or whatever, but we could rewrite it or refactor it to be better. So, how can we do that? Well, let's think back to what I said a minute ago. So, we had this many lines of code for each category of student. If we go back to the statement I made a few minutes back, tuition is simply whatever the student's rate is times the hours billed. Where the rate is determined by the residency status and the hours billed is determined by the number of credit hours taken. So, I could write something like this. If, and again, I'm not going to write the full code out, but if in county, then rate equals 118.34. If out of county, and I could write these as nested ifs, I could write them as a case statement, it doesn't matter. I'm selecting the rate based on the residency status. Then rate equals something else. If out of state, rate equals this. Then I could have an if statement to determine the hours. If hours is less than 12, hours billed equals hours. Else, if hours billed, if hours is less than 19, hours billed equals 13. Finally, else hours billed equals hours minus 5. Close all my if statements and then say tuition equals rate times hours billed. Think about that. There's only one place I need to get this logic correct now, as opposed to in the previous example, there were 3 places where I had to get that logic correct. So if something were to change, if they were to change the rule to say, we're no longer going to give the same rate for 13 through 18 credit hours, we're going to give you the same rate for 13 through 16 credit hours. Or 12 through 16, let's say. Let's say they adjust it that way. Then all I would have to do is change it in one place. Whereas if you had that block of code that did the if statements to determine what range of hours they fit in, if you had that code tripled in 3 places, then you'd have to go and change each one of those 3 places. What happens when you have to do a task over and over again? Human nature, you're bound to forget a piece, typo a piece. You've tripled your chances of errors. If you do that often enough, then the chances that you're going to introduce a bug when you go and change this, increases a lot. We could even make our tuition calculation really streamlined by breaking these 2 things into functions. So my calculate tuition function could be int hours billed equal determine hours billed. Double rate equals get rate. Return hours billed times rate. And then my determine hours billed method would have the logic to look to see what range they fit in. My determine rate would look at what their residency status was. But this function would be streamlined, so I could look at it and I wouldn't have to worry about the pieces I weren't interested in. So for example, if all they changed was the rates, if they were to increase the rate by $10 a credit hour across the board, right? All I would need to do is go to that get rate calculation, get rate method, and change the rate there. Boom, boom, boom. That's all I would have to do. If they were to change the bracketing for credit hours to say that it was 12 through 16, all I'd have to do is change this. I wouldn't have to mess with those other functions. I wouldn't even need to look at that code. All right? Because everything is broken down into a nice little function. That function does one job and returns the results. Yes?
Just putting the rates in the set variables, like outside of the code itself. Like let's say for in county, you had the rate set to 118.4.
Right.
That way all you have to do is just change that variable and it will change it throughout the entire thing.
Yeah, you could define a variable or a static variable or a constant for the rate, but you're still going to need an if statement to determine who gets that rate. All right, so you're still going to see, you're still going to have a method to go in. So yeah, in that case, if you're changing the rate, all you'd have to do is change the value of the variable. So yeah, that would be a real good idea. All right. All right, so I try to stress this in all my programming classes, that getting the right answer is only like part of your job as a programmer. Writing code that's maintainable is the other part. Maintainable code means easy to change. It means you can change it without breaking stuff. In old school programming, like when you had old COBOL programs and things like that, they used to call bad coding practices spaghetti code. You know, why spaghetti code? I don't know. I like spaghetti, but maybe not as a program. But why spaghetti code? Well, if you pulled at a strand of one code, you didn't know like where the other end of it was. And you pull something here and you might make a meatball topple over on the other side of the plate or something like that, right? Because everything was intertwined together, all right? And when things are intertwined together, you're not sure the impact of changing one thing. Whereas if things are broken down very clearly into their own functions, then I can go and I can change the rate without worrying about anything else, or change the manner in which the hours are bracketed without worrying about anything else. All right? So, We want to write code, object-oriented tools give us a potential to write much better code than we were able to do in the past, and we want to take advantage of those. All right, questions about this? Look at your own answer and look at my comments for Lab 2 if you've turned it in. If you haven't turned Lab 2 in, this should give you a good jump start of what you need to do or point you in the right direction. But for Lab 3, in addition to doing this, I want you to add a few constructors. All right, let's look at where we left off last time. Because last time, I think we talked about two key ideas, constructors and object reference pointers. So what I would like to do is bring up the example we had last time, talk about it, and then play around a little bit with these constructors and with these with object reference pointers to make sure that we understand it. So let's look at the example. All right, bake time for piece of 1 is this, bake time for piece of 2 is this, time for thick is this, time for cost for thick is that. All right, here is our pizza class, and here is our unit test class. Now remember, the idea of our unit test class is that we know that eventually that this is probably going to be hooked as part of a system that's probably going to have a GUI, and therefore we will use a GUI to create these objects and calculate the prices and so on. But until that point that we're ready to write GUIs, we need to test and make sure this is going to work. So we test this by creating a unit test class. It's going to just test our business logic classes. You don't have to worry about the code in your unit test being like good code. It's going to be, you're going to have things that are hard coded, right? And you want to have enough test cases to really thoroughly test to make sure that all possibilities are covered. In this case, I have 2. I probably would need more than 2, right? Because there's more possibilities, small, medium, and large, thin crust, thick crust, with pepperoni, without pepperoni. Probably 12 test cases would be the number that I would need in this instance. So I create the pizza. I use a constructor. Whenever you see new and the class name, I'm calling a constructor on the class. A constructor is what makes an instance of the class. It's what makes an object from the template. And we can write our own constructors so that we can not just create that object, but we can also initialize certain values. All right? In previous classes, we didn't write any constructors, because if you don't write any constructors, an empty constructor, a constructor with no arguments, is generated for you. That simply allocates the memory for your object. The constructors we write are going to allocate the memory, and they are also going to initialize some values. Now keep in mind that you write constructors for the benefit of other programmers. All right? In other words, you can supply information, you can allow them to supply information or omit the information. And if they omit the information, frequently you have a certain set of default values. Now again, in our case with pizza, I don't know if it's possible to really come up with a default pizza, but we did. All right? So I have two constructors, one that accepts the size of the pizza, one that accepts the kind of crust, and one that accepts whether it has pepperoni or not. So two strings and a Boolean. Our second constructor has no arguments. If we look at the code for that, our first constructor simply takes those arguments and plugs them in the attributes for that class. Our second one simply defaults the arguments, or defaults the properties to certain default values. In other words, if we don't say otherwise, the person's getting a medium pizza with thick crust and pepperoni. That's our default pizza. Now again, you could argue if that's not really relevant for a pizza shop. Do remember this is an actual example. I'm not going into business, so you don't have to worry about that. We can actually do slightly better than this. All right? We haven't talked yet about validation. In other words, how do I make sure that we give one of the legal values for the size of a pizza, small, medium, or large? Well, we're eventually going to put code in these set methods to make sure that. All right? So we should use those set methods everywhere, even in the constructor. So I can say this set size. This dot set crust. And finally, this all that this means is I'm calling the function that is on this object. Strictly speaking, I could eliminate that. And if I don't have this in there, it's assume this object. Whenever we make a function call, we specify the object that we're making a function call on and the name of the function. This is simply saying that whatever this is, whatever method we're calling, it's a function in this class. So I could do the same thing here. I could also do what's called constructor chaining, but we're not going to talk about that today. I could actually write it so that this constructor calls that constructor and passes the necessary arguments. All right. So we now have the price and the bake time. But when we create the pizza, we can create it and we can give it a value. All right. Let's play around with those object reference pointers. I'm going to go and do this. Keep in mind this code here is entirely for demonstration purposes. All right, I'm just demonstrating some concepts with you with this code. And we're going to test to make sure that we're understanding exactly how these object references and constructors and pointers and all that works. So to keep it simple, I'm not going to worry about cost or bake time. I'm just going to set some sizes, and I'm going to ask for the size back. So I'm doing system out println size is, and I'm displaying the size of pizza P. Let's try to get this all in one screen. So I'll make it just a little bit smaller. All right. I hope you can all see that. When this line runs, what is it going to say the size is for pizza P? We have a vote for S. Do we have other votes? All right, let's find out. All right. So let's go. Let's make sure everything's saved. And I'm going to compile it. And I'm going to run it. Tells me the size is S. So whoever said S got it correct. Let's make sure we understand why that is. Pizza P equals new pizza does what? What does that do? Okay, it creates an object. And does anyone know the special place in memory that it creates the object? What's that called? The heap. All right. What is P in this example, in this line? A pointer to that object. Excellent. So, if we're going to draw that, if we're going to represent that, it would look like this. Here's our heap. We created an object, and we set the size to L. We set the crust to thin, and we set pepperoni to false. And let's say this is memory location 2800. So the variable P would contain the memory location of that object. So it would contain, in our case, 2800. So we have our object on the heap, and we have our pointer that points to that object. All right? What does this line do? Oh, nope, you got to tell me without seeing the line. What does this line do? Okay. All right. Sets the pointer Q to what's in the memory for P. All right. That's true. Can anyone say this, put it in a different way? I'm not saying you're incorrect. I'm just wanting to see if people can say it in their own words. It simply copies a value of P into Q. All right. We define Q as a pointer to a pizza. So Q can put in, you can put into Q pointers to pizzas. P is a pointer to a pizza, so we can do this. And the way assignment statements work is we take what's stored in the right-hand side and store it in the variable on the left-hand side. Does this make a new pizza object? No. How could you tell that sort of at a glance? It doesn't say new. Exactly. If it doesn't say new, then it doesn't make a new pizza object. All right. We're not even doing that. We're just giving sort of a different name to refer to the same pizza. All right. Let's put it this way. Let's say if we were talking about, and again, maybe this is a bad example, but if I was talking about the BU building. All right? We'll make it simpler. Let's talk about the college center. The college in general, let's say. I could refer to the college, I could point to the college a couple different ways. I could say 1005 North Abbey Road. That's an address. That points to the college. I could give the latitude and longitude of it. That would point to the college. There's not two colleges. I haven't copied and had a clone of that college. There's simply two ways to refer to the college. The college that's at 1005 Abbey Road North, or the college that's at latitude, longitude, whatever. So in both cases, I'm pointing to the same thing. I'm just using different ways to point to it. I'm using different pointers. Sort of the same idea here. Yes?
Is there a logical reason you do that? I can't think of it off the top of my head.
To do something exactly like this code?
Well, to do like where P to Q have 2 pointers to the same object.
How can I say this? Yes, there's reasons to have 2 pointers to the same object. Would we ever write code that looked exactly like this? Probably not. All right, probably not. One thing that we're going to cover, probably not today, but next time probably, is we're going to talk about array lists, where we have an array list that contains a list of objects. All right, so we can loop through an array list, just like you can loop through an array. Well, we might want to grab that array list. We might want to grab an element in an array list, get a pointer to that element, and then pass that to another function. In which case, we would have different pointers pointing to the same object. But there'd be a reason to do that. All right. Again, code exactly like this is largely for demonstration purposes. Okay, so excellent answers to those. There is no new in this, therefore we're not making a new object. We are simply copying P into Q. And what is P? Or what is P is the address of that. So we now have 2 object references that point to the same object, which means that we sort of have 2 names for this object. We can point to it using P, or we can point to it by using Q. So if I say Q set size equals S, what I'm doing is I'm setting the size attribute of that pizza object to S. And the Q pizza object and the P pizza object are pointing to the identical objects. Again, not copies of each other, but the same object. So if I set the size to S, then now this pizza has become a small pizza. So in the line below, if I were to ask what is the size associated with the pizza that we pointed to in P, it would be small. Question? Yes. Well, this almost gets back to the question that the other student asked. Would we ever write code that looked exactly like this? No. This code is written to make sure you understand the concept of pointers. All right? And that if we did do something like this. Now, we're going to write code similar to this. Not today, but next time. And when we write code similar to this, we are going to be creating multiple pointers to the same thing. And if we change the value of one thing, or we look at the value of one thing, we're looking at the value of another. All right? Okay, let's change this around a little bit. Let me see, is this what I want? Yeah, this is as good as anything. There's an example in the book. There's like a question in the book where they create 5 objects and set this object equal to that object and all that. And again, it's really just to make sure that you understand in concept how this works. All right. What is the output going to be for this? Okay. It's going to be large. All right. Let's see if you're right. Let's make sure we save it. And it is large. Let's make sure we understand this. Okay. First line, pizza P equals new pizza, large, thin, false. So what does that do? Well, it does pretty much what we did before. Creates on the heap a pizza object. Size equals L. Crust equals thin. And pepperoni equals false. And P points to that. So, after the first line executes, that's what we have. What does this line do? The blank number 5, this one. Creates a new pizza object. Why does this one create a new pizza object where the previous example it didn't? Because it says new pizza instead of P. So, this creates a brand new pizza object. So let's say it is in memory location 3900. And Q is going to point to 3900. Now, what are the values for the attributes of that new pizza object? Exactly. Yeah, I don't remember them either, right? But how would we know? How would we find them out? We would look at the no argument constructor, because this is a constructor that got called here. Because see, I didn't pass it any arguments. Therefore, pizza, whoops, thanks. This is the argument, the constructor rather is going to get called because I didn't pass any arguments when I created this pizza. I said new pizza with empty parentheses. So unlike this one where I'm passing in those arguments and those get taken and set as attributes, here these values get defaulted. So the size of this guy gets set to M. The crust gets set to thick. And pepperoni gets set to true. All right? So that's how we determine. We have some default values in there. So again, this simply is a benefit to people that are making these objects. If you have information about the object, you can supply it. Otherwise, you're going to get whatever was defined as the default for that object. So this is what we end up with. We have 2 pizza objects. All right? Q equals P. Let me ask this question, or set size equals S. Q set size equals S. Well, that's pretty obvious. That will go and we'll set whatever Q points to. Go set the size to S. All right? So Q equals S. Q equals P. Let me ask the question this way. I'm going to ask you sort of a, I'll ask this question. When I'm done with this statement, how many pizza objects are living on the heap? 1. Why 1? Garbage collection. Let's make sure we understand why that is. So Q equals P. What does that do? That copies the value of the memory location named P into the memory location named Q. All right? So what is the value? Remember, the value is the pointer. So I copy into Q P. So now this guy points to this object. And who points to this object? No one points to that object. When there's an object that there are no pointers to, it's dead to the world, right? No one can refer to it. All right? There's no pointer to it. So it doesn't matter if it's there or not. And as it turns out, Java has a facility called garbage collection. And what garbage collection does is it looks to see what objects are out on the heap that don't have anyone that points to it. All right? So in this case, this object at location 3900, no one at the moment is pointing to. Which means it's inaccessible, which means the next time garbage collection does its thing, this object is deleted. Why is that important? It's important because it keeps memory it releases memory resources. If that was not done, then you would have these sort of garbage objects out there building up that you couldn't use anyhow because no one refers to them. If you don't have a pointer to an object, you can't use it. So without garbage collection, these objects would stay around just using up memory, and there'd be a problem. In fact, sometimes through sloppy coding, people keep pointers to objects that they don't really need, and sometimes that's called a memory leak, where you have an application that doesn't release the memory that it uses because it doesn't free up objects. It keeps pointers to objects that it doesn't really need. So at that point, there's only one object. All right? So both of them point to the object that's in 2900. So if I ask what the size is to that pizza Q, I get the value of L. Questions? So in a nutshell, how can we tell how many objects get created? We can tell that by counting the new statements. New, new. 2 pizza objects get created. Now here's the catch though. Are those pizza objects both around throughout the remainder of the function? No. What kills an object? What kills an object is when no one points to it. So, if I did this, how would that affect my answer? Pardon me?
I'm thinking you never created the object, so it's nothing there to point to. Taking Q and putting it in.
Right. Well, let's follow this through. The answer to this question is how would it affect this answer? It wouldn't affect this answer at all. Q still is going to have a value of L because we pointed Q to P. What this is going to have an effect of is, all right, let's just follow this through. We create pizza P, and it's stored in 2900, and it is large, thin, and false, and P points to that. We create Q, which has our default values, medium, thick, and true. that's in this other location. So Q points to that. So at line 10, that's where we're at. We have our two pizzas. One is pointed to by P, one is pointed to by Q. All right? Now, line 10 comes along and says pizza Z equals Q. Well, is a new object created? No, because we don't have the word new. So pizza Z equals Q does what? What does Z equals Q mean? It means copy the value of the memory location name Q into Z. So Z is going to contain a pointer to that pizza. Whoops. Now I say Q equals P. Well, Q is now going to point to this pizza, just like it did before. So if I ask what the size of Q is, it's going to tell me it's large. But the difference here is this. The difference here is Z points to this pizza object. So this pizza object has a reference to it, so it does not get garbage collected. So the only way this affects the answer is at the end of this function we have two pizza objects, one of which is pointed to by P and Q, one of which is pointed to by Z. Yes?
You don't have to declare pizza as a new pizza?
No. Remember, when you say new, that creates a new object. All right? This is simply saying point pizza Z to an existing object, the object that we created known as Q. Okay? So absolutely, we don't have to say equals new if we don't want to. We can grab a pointer and put it in a variable and then work with it. Again, keep in mind, I'm not even going to post this example. You have the pizza classes. It would be a good exercise to try to recreate this. We will go, next time we will do maybe something a little more meaningful. This was really just an exercise just to make sure you understood the way pointers worked and garbage collection and all that. Next time we'll talk about actually creating an array list, adding things to an array list, looping through the array list, grabbing pointers to things, and so on and so forth. Are there any questions for this? All right, we will see you in lab.